Looks like we're going. Okay, so last time we did barrel shifters. We went through basically you need at least three barrel shift. If you're an undergrad, you need an left barrel shifter. If you're a grad student, you're doing something that handle left or right barrel shift. Um, so that was basically where we left off at. I feel this is one of the bigger things. So if you have issues, um, what I want to do today is a couple ones we're going to deal with that have to do with addition, which might seem like a really easy thing, but we want to take a look at complexity, multiple ways of handling this, and then how do we construct them. So first, I'm going to have you today. This will be a fairly straightforward lab, in my opinion. We're going to do full carry. I'm going to have you do it by Genesis because we're going to make it open to however many bits you want. Since it could be as many bits as necessary, it has to be built based on those parameters as big as can be. Therefore, it's got to be built by a generator. Um, then we'll do two other types of ones that have different complexes. So let me first ask, before we get into this, anybody tell me what a triple carry out is?
Pulls on the reference cascading carries, I'm assuming carrying a bid, and adding to the 2D's probably binary.
Okay. So from that, you can figure out what's rippling. Yeah. So think for a second. We're going to use blue first. Um, so imagine for a sec you're adding, and let's just 1, 0, 1, 0, 1, 0. Is that fair? What numbers are those? 13. Yeah, let's just assume right now we're just doing straight addition. So we'll do binary. Binary. If you put in two's complement, what would that be? That'd be -3 against x. Right? Remember, with two's complement, essentially starting from the right after the first one, you flip the meaning of the bits. If the leading bit is one. So the top one is leading bit one, so it's negative. Um, I see a one far right, so the zero I treat as the other zeros. You're just going to stay once you understand that. Right? The bottom is leading zero, it's just right. You have to be comfy with them, however we do things. Uh, if I want to do this as addition, like let's do this old, grade school binary. Right? When we do this in our grade school but binary, I've got, a one plus a zero, right? And that gives me one carry nothing. 0 plus one is one carry nothing. 0 plus one is nothing, carry a one, right? And 1 plus 1 plus 0 is 0, carry a one. We usually only show the 4 bits. Right, in this case, we got an overflow. Right. Yeah, I'm gonna ripple here. Right, that's what's rippling. I am starting right, and each time the carry from the previous stage has to come to the next stage. And here it's starting left hand side because they're not going to carry it against you. So this is what's going to be a big this stage. Now the next part is the integration of each stage is identical once it's there, it's ready. Right? So in this sense, every bit is equally simple. All you have to do is just keep copying the same idea, just correctly hook it up later on. Right? Can you even assume that this first leading one here, even at a command, it's implicitly zero when I do an addition, right? Because I was stacking up. And just to make it all really true, again, make sense? So if I want to draw a circle, right, this is kind of like whatever it's grade school gives you for addition. And often you have to kind of set these type of things. And then ask what you now figure out how I want to build these formulas. Well, in essence, at every one of these stages, I'm taking these three inputs and I'm putting it into some type of thing, which I'm going to call a full adder. And what's coming out is a sum and a carry that's going to go technically to the next subdivided. We feel comfortable with that idea. And this one here was kind of like the carry in. We can call this carry out. Uh, and we can call this X and Y, just calling the top one the appropriate X. Yeah. So from that circuit perspective, this is all we need to pull out. If I took this static state circuit and shift it up, hook it up to just all of it to work. Again, assuming you know what full adder does. Okay. All right. Now, in the past, how did you develop the full adder? You get this in. But then, it's not the usual first way. That they showed you how we just say, like if you were a kid adding this together, you're not going to do 300 about who here's the answer. You're going to take two of the numbers and say, let me add those together. And you're going to partial sum. You'll add an extra digit to your function. Is that the case? So usually what we would do is we would look at this and we go, oh, let's break this up. You know, inside the full adder, here comes X and Y, and here's carry in. Right? And out comes my carry out, my son. And I could say, well, let me put these two together in a thing I call the half adder, right? And it's going to have a temporary sum, and I'm just going to put a temporary carry inside. Right? And then of these, I'm going to take this carry in, and I'm going to have to add it to this temporary sum. But I have to add 2 bits, so I can put that in another half adder, right? And I can get a carry out of this also, temporary carry number 2. We'll have to figure out how to combine those, but the sum out of this is the overall, right? And then we look at these and we say, how to combine these two carries? Well, I generate a carry here in what case? They both have to be, right? And if both of these are 1, I'll get a 1 here. What will I get there? A 0. So can I get a carry here and a carry here? No, it's impossible. So, right? So one of those two is, right? And as long as one of them is, I should pass it in. So that fits actually with the exclusive order. It also works perfectly fine with text, right? So technically speaking, you can do this purpose. Since or is a little bit faster, I'm out for an order. Also, and it could be because it's the general, right? it just may be as you know what's inside them. I think actually just nicely go in, make it easy to be done with this, right? This half adder, I've got an X and a Y coming in, and my half adder needs to have a carry and a sum bit coming out. Most people do sum and then carry. I go home short axis every single one. I want to make the case now that those books are like what they do. So this is by far the most common I actually haven't found a fault that this is previous for that. But I'm gonna make my case why it's wrong. When you write something, when you think about this is going on inside of here, right? I added these three numbers and I got a one carry a zero. I just treated them as two zeros. But in reality, what it is, those numbers here in this column, I added 0, 1, 1, and I got 1, 0, 2. So they would be separate. If you put carry sum, this is the most significant bit, this is the least significant bit. And you bring up the standard order that you roll numbers. Now it's just any numbers. Right? Typically, people just put in the bit, the carry bit, and they move on. And there is no thought to what those bits mean. So I strongly suggest you don't follow that pattern, you follow this pattern, where it just makes more sense. Now, if you think about this, all I'm doing when I'm making this table is adding 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 2. Right? It's just, it's not like it's difficult before, but this is just stupidly easy and it's really easy to check. Right? And then all we do is we look at these. Anybody recognize this pattern? That's an AND gate. Right? Anybody recognize this pattern? That's an exclusive OR. Right? So all you need is one gate for each inside a half adder. Right? So my half adder will be made up of a carrier, which will get an AND gate. I'm not going to write HA on this. Um, my Y bit coming in, my X bit coming in. And this one is now my carry bit coming out. And then I have an exclusive order that I can draw neatly. And that exclusive OR comes out to the sum. So it's trivial to then do that afterwards. Hopefully this is all familiar stuff. You don't need to redraw this. I look at handwriting. It's actually reproduced within your lab manual. So if you look inside uh, the lab manual, you see that it shows you this lovely picture. So, and this is hopefully just a reminder of what you did with your basic digital logic. It should have logged you the ideas. It's pretty to do a half ladder to a full ladder because it shows what part of the street needs just check. It's called bottom. You build small things, you build larger things, those things. In this case, I'm not going to do that. This is cute to learn, but it's much more efficient to actually build directly a system. And there were several ways I could do it. I could have done this truth table right over here, right? I could have gone in and done, whatever, made a table that was X, Y, and CN, and, output is carry and sum, again, pointing to the right thing. This is my carry out. Right? All I'd have to do here is just, treat it just like my normal addition. see. It's a little reference line, so I don't waver, right? 0 plus 0 plus 0 is 0. 0 plus 0 plus 1 is 1. 0 plus 1 plus 0 is 1. 0 plus 1 plus 1 is 2. 1 plus 0 plus 0 is 1. 1 plus 0 plus 1 is 2. 1 plus 1 plus 0 is 2. 1 plus 1 plus 1 is 3. Right? And I can go in, I can even recognize these things, or I can do Carnot amounts, or whatever floats my boat. I'll do this. So I can just have done table place instant and just build the company. Right? Now, which I'm the assumption and we're going through this picture about the issue. There is one that doesn't all the things get recognized. Some of it's technique. So when these types of happenings, you can often just notice what's going on because you recognize something. And it's built something that does that. Right? To get a sum out of all these bits, when you get a sum, you, but what if there's I'm just saying, if you were looking at this larger pattern, you could do 4 because it's not just if there's two or something. There's something I'm gonna have to get when there is just not exactly. So now, do we have a key that that's what exclusive are actually is, right? In truth, when you exclude, it does unnumbered bits, right? At two, that just works out to be different, which is what we usually think about, right? But the reality is, if you design a goal that's more than just two, and it will keep it steady, and it will not. So then full design thing, exclusive or, I can recognize this. This is still XOR, right? Or the circled plus, whichever way you like it, right? Now, this is where your answer, right? So how about carry? It's pure, right? Now, this is a little bit unclear, right? So, I mean, you could just look in chat if there's at least two, right? So I could walk through and just take a look at on here and see X and Y. I could check, X and C in, and I could check Y and C in, and I could OR these all together. And I could tell, we agree. So I, I could do this. This is really still, right? Taking this and just ORing them, right? Uh, XOR and Verilog is just, so I could make these very easy how to just do a full add. Now, we don't usually just want to do addition. Addition and subtraction are related functions. Okay. But yeah, actually, it will be the case. Because when we want to do subtraction, we build another piece of material. So I want to take an atom and I want to build in a way to negate one of the numbers. Which number am I supposed to negate? The second, which I'm calling, right? So how can I get minus y? Yeah, so there's a few ways to we agree. So what what's any of the way that you can put it use? Well, that's not a totally fine. Right? So I try to all once, get the result in the end, right? Actually, that's the same thing, but it's conceptually a different way of thinking. And might help you make a different survey. In this case, it doesn't, but it is good to think about those possibilities. Is there any other way you can do this? Like on the right and copy this up to the first one and then flip every bit down. For a human, that's actually really stupidly easy to do. Uh, so as a human, if I gave you something that looked like, whatever, 0, 1, 1, 0, 1, 0, 0, right? It's stupid. Yeah, I mean, really make you stupid. Right? Now, if you're looking at this person and you had all the data and everything, because I could just walk in and just go copy up to and including the first one and then flip everything after. Boom, done. Right? That absolutely, that's, that's the easiest. Right? What do you do then as a machine? Well, that is to build a conditional and when the first one occurred in the original one, you're back. I could do on every bit. Yes. And this underscores one of the basic things. You are not a machine. What is easy for you is probably going to be very hard for the machine. What is very easy for the machine is also going to be easy for you. This is called a fault theory inside computers. So in computer design, this is both the hardware and software. Usually what is easy for a human is hard for a machine and vice versa. Right? Have any of you ever looked at a piece of code and you're looking at it, what in the heck does it do? It seems to make no sense. You look it up and it tells you, this is, when you're looking at it, this code does that. Because there are algorithms confusing the heck to us and computationally probably Phoenix when it needs to be very efficient, what computer can do that. Computer can do that large mindless amounts of algorithm. How are you using mindless amounts? Yeah, it can be 50 random numbers. Student, right? I guarantee you by the end of this, you're going to be like, hey, my guts and the spicy life. All this, right? And that's only 50 numbers. Right? True. I mean, that's not big yourself a painless task or just calculation, right? I, I, I don't even tolerate adding 5 numbers at this point in my life because it's just a waste of my time, right? I'll look at it and ballpark it. I'll do all kinds of stuff. I hate actually having to think because why should I? Right? I can look at things and make a guess and be, I should have changed. I'm good at that stuff. You just can't do that. We're just good at different things. This is why I told people that you'll never be replaced by a machine unless what you did is train yourself to be a machine. Then the machine will kick your butt and the machine has every single stupid right? But that's because you did something dumb or maybe necessary at the time, but not playing strong suit. Right? As a human, you do things that a machine will never do. Your brain is built and it's good for some people and some are better gift. Each serves the purpose. Now, your job, however, is to think how will the machine think about things. So you're gonna have to try a lot of different outlets, even if they look weird, and you have to see which one plays. Now, in this case, is flipping a bit easy. It is blinding these, right? I mean, if it's even the machine, right? Flipping a bit is not the case. How about conditionally flipping a bit? I mean, what if I had a signal called flip and then I had an actual bit, right? I could put in don't flip the bit or flip the bit, right? We agree? And then here is, right, I always do two lines to say my output's coming, right? Then I have the conditionally flipped bit, right? Well, if I'm not supposed to flip a bit, I just copy it. Here I'm supposed to flip the bit, so I just flip it. And I recognize them sort again. So not always flips it, and XOR conditionally flips. It gives you a thing to say or don't flip it. Well, it's really stupidly easy to do flip a bit. This is often one of the very common uses of XOR. I mean, remember how we talked about negated products and something? Remember with the negation, we have to flip bits. Guess how we do that? Excellent. Actually, that's usually built into your FPGA, right? So if you wanted to do that thing built within that conditional logic block, you'll actually have an XOR to the output, right? With a memory state, and you just see it's a negated function. So it becomes stupidly easy then to be able to teach these logic things. They're not. That makes them nice. But I need to actually build anything extra to add one. Can you tell me why I don't need to add anything extra to it? Something I mentioned early on. This first input thing, was I using it? Now, to make it simple, I just put the zero there. I can put one and I need one to put the bit. So whatever that signal is, that becomes I'm subtracting. It becomes one into the extra. And it becomes an extra carry, the first carry gets on this. Now it's turned into two. So, yeah, it's really, right? Sometimes always. So you see a lot of others, you'll see an amp, a bit, and it comes because these all the XORs. It also gets put as first carry in, right? All it is flags. This is subtraction. Well, it functions correctly. You flip the bits into one, you subtract. It won't flip the bits into zero, and then the bit coming in, if it was zero, it puts a zero into the significant bit, right? And if it's subtract, it puts a one in that, which has one, and it finishes all these helpful. I don't need anything extra. So, excellent. Here, I stick with you. Does that make sense? So if you think that this is kind of actually a cool thing. So I've got this XOR, right? And I can build that as my full adder. And now all I need to do is to flip the bits appropriately and set up the carry-ins right. So I'm going to kind of do this as a little prettier thing now. I'm just going to draw this as a bunch of full adders and prove that I am not an artist. Right? And inside each of these full adders, I'm going to have a series of things. Now, I'm also going to have my carry ins come in on this side. That way I can do this for all my carries. And I do that last one down in case you want to keep that. That's your extra bit. I'm just doing four here, right? But I literally, the carry out of one becomes the carry in of the next. Right? These are all little full adders. And I'm just going to run my X and Y in here. And this would actually be the appropriate bits, right? So X and Y. This is X0 and Y0, X1, 2, X2, 3, X3. We agree? The very coming in, I might have to give as the mode bit. I'm just going to use M for mode. Right? But all of these are also going to have the mode bit coming in for this extra little position to do the add subtract. So this is technically not a full adder, it's technically a full adder subtractor. If you really want to be technical, like out there. And then what comes out is the appropriate sum bits. Some 0, some 1, some 2, some 3, and this is my overall carry out. It's kind of a cool thing because now you know how to make someone. Stupid jumps that appear within digital logic. Right? Oh. Now, how do I build these full adders? Well, we've got only a few basic equations for any one of these, right? If you just count each of these names coming in, right? This is carry in, this is carry out, this is my sum, and I've got y, x, and a mode. Talking about subtract. We know a few things from what we did before, right? Uh, so the mode bit is not used inside here because I have a specific carry in. Well, first off, I can do this to calculate my carry out. I know carry out is equal to my x, dotted with the y. I'm going to do this ampersand style because that's all right. We better? Awesome. So I'm just going to take these. I'm going to do the ampersand. Why am I doing ampersand? Anybody? Yeah, exact. That is my exact reason for it. Because I'm trying to put this into Verilog syntax. And I've got y ampersand c in. So I have calculated for you that's in here. And I'll actually have one other thing to suggest something. I might change my y to yt. Right? Why did I need yt? Yeah. I think I bought it after I conditionally flipped it. So I'm going to YT. Right? I need to use that for my like that YT. Well, now you got all the names for me, right? Okay, can you tell me the Verilog syntax? T, Y, here or Y. Exclude the word. Oh, take left. Whatever we call it S internally. Somebody help me with that one. E, E, X, one, X, yeah.
for.
I'll have to wear it down. What am I trying to excellent with? YP. Forget your T. Because we need everything that has been conditionally equipped. If it's open, we want people to be at. Equipment. So, this is now the definition of your full app. Agree? No. Therefore, I can just copy these down. Well, sort of yes and sort of no. What's the only challenge we have when we want to build these things? What's that? So the length shouldn't be too horrible unless you get really ugly names. But even that just carries a multiple. So I could technically make each of these ones. I could C0, I could say C0 equals, and have, some X thing, next the ampersand, some E thing, new only, and then do it for new, and I'll get but it'll be pretty there, and it'll still be readable. Neither break up to units. If I have the pluses, blank space is really good for readability. So if I do a plus on it, every time. So I can handle.
So what was called here is the question is going to be where originally.
Yeah, I'm gonna do a generate. What's gonna be the challenge when I go to generate?
Go to generate your X will be changing, Y will be changing.
Yeah, and these will be changed because it's now gonna fit within a larger structure. I can't just use CI and CN, right? Because CN one becomes CN for the next one, right? And if I only do things up, they're all combined together. Short. So I have to figure out a naming scheme. Now, not every variable has a problem with this. Right? What's the easiest variable? Yes. Make it stupidly easy, right? Because it doesn't take variable all of them up together, right? Challenge for that one is putting it in whatever you see in the first one. But that being, I was making a final statement, whatever I call the end, I just equal it to mode and done. So mode of these. What's my next piece? Sum is pretty darn easy also, isn't it, right? Because it's just going to be sum, and then whatever its appropriate locations, right? Sum zero is one, I got to use across five. All that to do is some square brackets and add an index. So I agree. That one is also very, very easy. Much easier. I think Gary is more challenging, but it's hard. Right? But how to do these patterns when we do get to when it gets bigger. You'll be better at this. Right? So that's why I want you to think about the names. Right? We're going to have a very fun way to do these additions, what we call conditional sums, but it's going to get ugly with the wires. Harry is also get really ugly. So the names will not be as nice. So what else is pretty straightforward. About six difficulty levels. X and Y, yeah, just you literally just whatever your index is, you just put the square example with the index on them. Right?
So place X and X Y is going to be in A to C I.
I just put X, Y, right? Same thing for Y. And I've already got that handled in. Your YT again, you'll just put it and just do that same thing. They're already in.
if the bundle of the bundles be also be carried.
So I don't necessarily need to. This is where we have to do a little bit of how do we handle it. How do they handle the first carry? Okay, so I need an array of carries. Let's call it zero. Right? So what would I do with a piece of it? Yeah. So I just say, somebody in C, zero. You can do that for the generator, it only happens once. So I don't need to do this repeatedly, right? How about the last one? So this is kind of like a barrel shifter, right? Except the barrel shifter had a number of bits. This one here has one that's speed. So it's nice. So yeah, that varies. So all the bits plus one in this case for the carries, and the very least one, right? That one I would just assign carry out to be equal to my very last bit of the carriage. Yeah, if I tell you 16 of these things, you'll have to 16 bits. You'll just tend to, P as defined from 16 to 0, plus 1 instead of 50 to 0. Right? So I would just make whatever the last one is and hit the carry out. Right? And then when I'm going through my for loop, I just have to say that I'm assigning CI plus 1 to be equal to, and for that CI, I would technically, for each one of those, I call it carry out there. I replace it by CI plus 1, the next one, the index will be equal to, and if it's CI inside, it would be CI. Because I just be starting with 0 and generate carry 1, and then I take carry 1 inside and generate carry 2. So inside the for loop, that's the most complicated one that's in there. You just need a CI plus 1 on the left hand side of the CI. That makes sense? Okay. Fully, I want you to generate it for me. And we have enough time. We have about 30 minutes. We're going to do this class here. We're going to learn trying to create this code here. So we would like to stop 5 minutes before the end, and you guys can talk and share your code. We'll discuss it then as we do. Right? Okay? So I will circulate around. I'm going to stop the video at this point. And this is almost occurring, and you won't be able to hear it anymore. And I'll try to remember to start back up at the end. I would appreciate help and try to remember that. So I'm just going to pause it right now. So my screen returns.